Now the next now the next topic that we have to learn is bond energy. Let's define bond energy first. So remember that bond energy is also a type of energy. So the unit would be kilojoules per mole, and the symbol most of the time is used as Be, bond energy. All right, so bond energy. Now, what is bond energy? Remember that in our syllabus, this is a very important note. We always define bond energy in terms of breaking a bond. All right. And if you want to break a bond, if you have a pencil and you hold it in between your hands, right? You grab it and you hold it in between your hands. If you want to break that pencil, would you have to give energy or will you get energy?
You have to give energy.
Yep. So if we define bond energy in terms of breaking a bond, and breaking a bond requires energy, so bond energy for us should always be exothermic or endothermic.
And endothermic, right?
Yep. Always endothermic process. All right. So we always define it as endothermic. All right. So the definition is bond energy. It is the energy absorbed or needed to break 1 mole of a covalent bond, 1 mole of a covalent bond in its gaseous state, in its gaseous state. Now it is very important that the covalent bond must be in its gaseous state. All right. This point is very important, that the covalent bond, so the covalent bond must be in its gaseous state when you're trying to break it. And what you're doing is you're breaking 1 mole of a covalent bond. All right. So how do we
Yep.
write the equations? So it's basically breaking this covalent bond over here, this covalent bond, but this covalent bond must be in its gaseous state. And when you break this, these two atoms which were covalently bonded, now they're not bonded to each other, so they become isolated gaseous atoms. All right. The bond between them breaks, so they convert into isolated gaseous atoms. So I can also add this in the definition. So energy absorbed and needed to break 1 mole of a covalent bond in its gaseous state to form isolated gaseous atoms. That's bond energy. All right. So now how many gaseous atoms do I get? I get X gaseous and I get another X gaseous. So I can simply write this equation as X2 gaseous, which has a covalent bond inside it, forms 2 times gaseous atoms of X. So this is how I would write a general equation for bond energy. All right.
Yep.
All right. So now what we talk about bond energy, when we talk about bond energy has 2 ways of defining it. There's either in terms of breaking a bond or in terms of formation. In our syllabus, we always define it as in terms of breaking, not in terms of formation. But you should know that it can also be defined in terms of formation. All right. But remember, if bond breaking is an endothermic process, that means it requires energy, then bond formation would be what kind of a process? It would be exo. It will release
Exo.
energy. Yes, it would be exo. It will release energy. All right. But do remember, whatever energy is needed to break a bond, that's the same energy that is released when that same bond is formed again. All right. The same energy is needed to break a bond, and the same energy is released when that bond forms again. All right. So I can write as I can write this as energy needed to break a bond would be equal to energy released when the bond forms. It's exactly the same. The only difference is when you break it, you have to provide that amount of energy. And when that bond is formed, it releases the same amount of energy. So if I needed to break a bond, for example, between these two X atoms, and I needed to break this using 100 kilojoules, right? The same
Yep.
energy would be released when this bond forms again. It would be 100 kilojoules again. But since it is released energy, it would be negative 100 joules. And since I was breaking the bond over here, I have to provide 100 joules. Clear?
Yep.
So bond energy is basically in our syllabus, we always define it in terms of endothermic process, in terms of breaking, and it is always positive for us. It's never negative for us. All right. So you have to remember that in our syllabus, it is always defined in terms of breaking. You always define it as the energy needed to break a bond. All right. And all the values, even in our data tables, are positive. That means they're all for breaking the bonds. All right.
Yep.
Now let's write some example equations for bond energy. If I want to write the bond energy for the equation for the bond energy of chlorine, how do I write that? So I'll write Cl2 gas, right? Cl2 gas, chlorine is gaseous at room temperature, that is gaseous diatomic molecule. So I'll write Cl2 gas breaks into what? Two Cl gaseous atoms. This is bond energy. This energy change over here represents bond energy. Why? Because these
Okay.
chlorine atoms are a diatomic molecule. And this covalent bond over here is in gaseous state because chlorine is gaseous at room temperature. So now at this time, if I break this bond over here, it will convert into two chlorines gaseous isolated atoms. And since I'm breaking this bond in its covalent gaseous state, that's why this is bond energy. The energy required over here would be equal to the bond energy. All right.
Yep.
What about if I want to write it for iodine? If I want to write the bond energy for I2, then I have to have iodine in its gaseous state. And then at that time, if I provide the energy to break this bond, that would be bond energy. These two iodine atoms would break off from each other and convert into isolated gaseous atoms. At this time, this is bond energy, but iodine at room temperature is not in gaseous state. It's a solid molecule. So if I try to break this solid molecule into 2I gaseous, do you think this is bond energy?
If it's already single, it's the I2, right?
Yep, it's I2.
And it's broken down to I. So yeah, right?
Yeah, this is not bond energy. Why? Because this covalent bond over here is in its solid state. And how did you define bond energy? It was the energy
Oh, and it's
absorbed and needed to
gaseous
break
state.
1 mole of a covalent bond in its gaseous state. So this is not bond energy. This energy change does not represent bond energy because this covalent bond is initially in its solid state, not in its gaseous state. Yes, if I have iodine gaseous and I break it into its gaseous atoms, gaseous isolated atoms, then this is bond energy. But the second equation, this does not represent bond energy, it represents some other energy change. Why? Because initially, when iodine is in solid form, when I provide heat energy to it, it will not break its bond. That heat energy will not be utilized in breaking the bond. In fact, it will be utilized in converting iodine solid into iodine gaseous. So there's been energy being used over here that is for vaporization, right? And then after that, if I provide energy when iodine is in its gaseous state, and then that energy is going to be used in breaking the covalent bond and then converting into 2I gases. Right? So iodine, solid to iodine gaseous atoms, that's not bond energy. That's some other energy change which involves vaporization and bond energy, both of them. All right. So it's greater
Yep.
than bond energy's magnitude. So that's why this is not bond energy. What about sulfur? If I want to write the bond energy for sulfur, how do I write it? Now, sulfur is S8 solid molecule at room temperature. So if I write S8 solid 2, sorry, not, so sulfur gaseous atom, how many sulfur gaseous atoms will form? 8 sulfur gaseous atoms will form. Is this bond energy?
Yep.
No, it's not bond energy. Again,
Oh, because
why?
it's in solid form, right?
Yes, yes, because these bonds between sulfur over here, the 8 sulfur atoms, are what? These covalent bonds are in solid state.
Yep.
So unless and until sulfur is in its gaseous state, I cannot say this is bond energy. Because the initial energy that you actually provided to be the bond energy, that is going to be utilized in changing the state to gaseous first, gaseous molecule first, and then it's going to start breaking. So that will the energy required to convert sulfur solid into sulfur gaseous atoms, that it will be larger than the actual energy needed for the bond energy. All right. So if
Okay.
I want to write the bond energy equation for sulfur, I'll make sure that I'm starting with the gaseous molecule of sulfur, so that all the covalent bonds inside are in gaseous state. So now when I break it, it will convert into 8 times S gaseous isolated atoms. Now this is bond energy because I'm starting with the gaseous state of covalent bonds over here in this molecule. Clear?
Yep.
So what about bromine? If I write Br2 liquid goes into 2Br gaseous, is this bond energy?
No.
How would I write the bond energy equation for this covalent compound?
It has to be gaseous.
Br2 gaseous breaks off into 2Br gaseous. Now this is what this energy change would represent: bond energy for bromine. Why? Because this covalent bond over here between the bromine atoms is in gaseous state. All right.
Yep.
So this was our bond energy. What about oxygen? Oxygen is in O2 gaseous form. So if I break this into 2O gaseous, is this bond energy?
Yep.
Yep, because the oxygen-oxygen double bond over here is already in its gaseous state in oxygen gas. So now if I provide energy to break it into gaseous atoms, then this is bond energy. All right.
Yep.
What about phosphorus? Phosphorus is P4 solid at room temperature. If it goes into 4 times phosphorus gaseous atoms, is this bond energy?
No, it's not.
It's not bond energy. But if I want to write the bond energy for phosphorus, I will start with phosphorus gaseous gaseous molecule, and I'll break it into gaseous atoms of phosphorus. Now is this bond energy?
Yep, it is.
No, it is bond energy. So are we clear about bond energy?
Yep.
Now we also studied another energy change in which we were forming gaseous atoms just like we're forming them in bond energy. What was that energy change? We studied
We
that
were
energy change
forming
yesterday.
what?
We
We were
studied
forming.
another energy change in which we used to make gaseous atoms.
Oh, atomization, right?
Yeah, atomization. But there's a difference between atomization and bond energy. So we should know the difference between atomization and bond energy. So bond energy, and let's compare atomization. Atomization, that was delta H naught of atomization. Now, the similarities between both of them. What are the similarities? Both have the same unit, kilojoules per mole. Both have the same unit, kilojoules per mole. But how do you define bond energy? Yep.
of the gaseous atom, right?
One mole
Is going
covalent
to,
bond in its gaseous state is
yep,
broken to form gaseous
the atom
atoms.
and gaseous atom.
Yep. But what was atomization? Atomization was the energy absorbed to form 1 mole of gaseous atom. It was very specific about 1 mole of a gaseous atom, right?
Yep,
From
from its
what?
elements
Yeah,
under its standard condition.
from element under standard conditions. Very good, right? So there's a difference between both of them. Now, if I talk about the bond energy of, for example, let's take, which was the last example we did? It was, let's do bromine. If I talk about the bond energy equation for bromine, where should I start from? Br2, but in what state? Yep, in bond
In
energy,
gas,
it's gaseous state. Gaseous molecule will break off into how many bromine gaseous atoms will I get over here? Whatever the equation
two.
requires, right? I'll get 2 over here. But if I want to write the atomization equation for bromine, that would be to form 1 mole of a bromine gaseous atom, 1 mole of a bromine gaseous atom from what? Its element, that is bromine. Under standard conditions, it exists as bromine liquid. Under standard conditions. So this would be atomization, the energy change of
Yep,
atomization over here. So there's a difference between both of them. And bond energy is starting from a covalent gaseous molecule and breaking off into gaseous atoms. But in atomization, you're making a gaseous atom, 1 mole of a gaseous atom, but you're starting from the element in its standard state. And bromine at its standard state at room temperature conditions exists as a liquid, not as a gas. But in bond energy, you start from bromine gaseous. So there's a difference between both of them. All right.
yep,
What about phosphorus? If I want to write the bond energy for phosphorus, phosphorus exists as a P4 solid at room temperature. But if I want to write bond energy, I would have to start with P4 gaseous molecule. I make 4P gaseous molecules. This is bond energy of phosphorus. But atomization of phosphorus would be different. Now the atomization, I form 1 mole of a phosphorus gaseous atom from its element under standard conditions, which is P4 solid under standard conditions, right?
yep,
Now, I did not balance these equations. So if I want to make 1 mole over here, the definition says 1 mole over here. I have to write 1/2 over here to balance this equation. And in the second equation, if I want to make 1 mole of phosphorus gaseous atom from its element under standard conditions, which is a P4 solid molecule, I will have to write 1/4 over here to balance the equation. Clear?
yep.
So this is what we need to know about bond energy and atomization. Keep them both separate from each other.
Okay.
All right. So now for questions related to calculations. If all the data in the question is for bond energies of all reactants and products, use this equation. Do not make any cycle. That will make it even more complicated. What you want to do is you want to use this equation. So the enthalpy change for any reaction, you can find it from here, would be equal to the energy given in to break the bonds of reactants. All right. Energy given to break the bonds in reactants plus energy released to form new bonds in the products. Now let me just clear this out. Remember that energy released will have what sign?
Negative.
Negative. So all these values should be negative, right? And energy given to break the bonds would always be positive values. But in the question, will always be given positive values because we define bond energy as in terms of breaking. Even for the products, you'll be given positive values. All right. So how you can simplify this formula is delta H naught of reaction would be equal to energy given in, which is positive, and its do plus minus would be minus energy given out. Now this equation is simplified. Now you do not need to consider any sign when you insert values over here. Just insert whatever value is given into the question. Sorry, into the formula. All right? If you memorize this formula. But the original formula is plus minus energy released because energy released should be negative. But if I open that formula and I simplify it, that plus minus becomes minus, and now you do not need to consider any signs while plugging in values over here. Just plug in all the values that are given in the question. No need to write the energy released or given out as negative over here. Clear?
Okay.
All right. So if you want to use this equation that I've given you, this first equation, this one, then you have to make sure that whatever values you write over here, they are negative because that's energy released. But if you use this equation, I've already catered for this negative sign over here. Why? Because whatever values you'll put over here, they'll multiply with this negative sign and become negative, right? So it's already catered for. So it's better if you memorize this formula instead of the formula over here, but you should know this formula, that it's plus minus the energy release. And when these plus minus multiply, it becomes negative. And this formula is generated from that. All right. So this was the formula that you needed to memorize. But why have we written energy given in to break the bonds and energy given out when bonds are formed? So whenever a reaction occurs, if I have two reactants, let's say I have A and B. This is the last thing that we'll do today. So we have reactant A and we have reactant B. And we have to form the product AB. All right. So I formed 2 moles of AB over here. Let me just write it as 2 moles. So AB is being formed. What's happening in this reaction? What's happening over here? What would this delta H be equal to? Let's do that. So first, when these reactants come together, they'll do what? They'll break these previous bonds between them, right? These
Yep.
reactants which have their older bonds, will have to break these bonds in order to form new bonds. So this is where bond breaking is occurring in this reaction. On the reactants, bonds are broken. So this is the endothermic process, the breaking of bonds. So this is the positive part of a reaction, endothermic. And then when the new products are formed, when these bonds, new bonds are formed, then energy would be released, right? Because bond breaking is endothermic, bond formation is what? Exothermic. So over here, bond energy is released, right? So energy is released over here in bond formation. So it is exothermic, negative. So in order to find what the enthalpy change of the reaction is, what will you do? You'll find the difference in these energies, right? You'll find the difference in both of these energies. How much energy was used in bond breaking and how much energy was released in bond formation. So delta H would be the difference between breaking the bonds plus formation of bonds. Or minus formation of bonds, right? So that's why we say energy given in to break the bonds in reactants and energy given out when formation of the bonds in products takes place. Are we clear?
Yep.
So it's always energy given in minus energy given out. When you revise this formula, then this minus sign caters for any sign changes that you have to put over here. You don't have to say change the signs over here now. Just plug in the values that are given in the question for bond breaking and for bond formation. Just plug in the value. All right.
Okay.
Now, it's just one example. I will not give you any values, but you should be able to do this. So the FAQ would be N2 gas plus 3 moles of H2 gas goes into 2NH3 gas. Now what we have to do is we have to find delta H naught of reaction for this. How much enthalpy change of reaction is given. And let's assume all the bond energies are given in the question. What would you do? You will not make any cycle. Go with the equation. So bond enthalpy change of this reaction would be equal to delta H naught of reaction would be energy given in minus energy given out. Now, in order to figure out what are the energies given in, you have to open up these molecules. N2 is nitrogen triple bond nitrogen. So you have 1 mole of N2. You have 3 moles of H2. One hydrogen molecule has 1 hydrogen bond. So 3 H2 bonds, 3 moles of H2, that means 3 hydrogen molecules, 3 moles of hydrogen molecule. And NH3 is nitrogen, hydrogen, and hydrogen. And you have 2 moles, so 2 NH3 molecules. Right? Now I've
Yep.
written all the reactants and products and their bonds. Now I know what bonds I have to break, what bonds I have to form. So what will I do now? First, I'll go in the energy taken in to break the bonds and reactants, and then the energy given out in the formation of bonds in products. And since I've written negative over here, I've already catered for the negative sign of the energy released. So I do not need to write a negative sign inside the bracket anymore. All right. So energy given in. What are the bonds that I want to break over here? I want to break this nitrogen-nitrogen triple bond, right? So N energy is 1 times I want to break the nitrogen-nitrogen triple bond. Whatever bond energy it is for this, I'll insert the value over here. Plus, how many hydrogen-hydrogen single bonds do I have to break? 3 times. So plus 3 times the hydrogen-hydrogen single bond I have to break. And I'll insert over here whatever the bond energy value is for the hydrogen-hydrogen single bond. Okay? But you need to be
Yep.
able to make this equation first. All right. So I'm done with the reactants. I've broken all the bonds. And then minus, what are the bonds formed in the reactant side? It's nitrogen-hydrogen single bonds, right? They're nitrogen-hydrogen single bonds. 1, 2, 3, 4, 5, and 6. So 6 times the nitrogen-hydrogen single bond is being formed in the products. I'll insert the bond energy value as it is because I've already catered for the negative sign for the release of energy over here. Just insert the bond energy value. So once I know what bond energy value is for this, and for this, which will be given in the question, I can find out by solving this equation now the delta H naught of reaction. All right.
Yep.
That's all for today. We'll continue this tomorrow, in which I'll give you the bond energies and we will solve this for delta H naught of reaction. All right?
Okay.
Okay. And I told you in the last class that whenever you're given bond energies in the question, never think about making a cycle. Simply do what? Apply the delta H equation. What's the delta H equation? It is delta H of any reaction would be equal to energy given in to break the bonds minus energy given out when new bonds are forming. Right? This is the equation for delta H.
Yep.
So whenever you have bond energies in the question, never make a cycle, just apply this equation and solve the equation, solve the question. So, but in order to do this, you need to know the structures of the following. So you have a carbon over here, it's bonded to two hydrogens, it forms a single bond with each hydrogen, and then a double bond with the other carbon and two hydrogens, single bond with two hydrogens. So this is the structure of ethene. HBr has a single bond in between them. And then you have CH3, CH2, CH. So you have two carbons, you have a bromine over here, you have two hydrogens on this carbon and three hydrogens on this carbon. So now you know the structures, you know which bonds are going to be formed and which bonds are going to be broken. But just to stay safe, if you want to just look at the bonds which were broken and the bonds which were formed, that's another story. What I want you to do initially is break all the bonds and form all the bonds. All right? Don't just
Okay.
go to the bonds which were broken and which were formed, break every single bond and form every single bond initially. All right? You'll always get the same answer. This answer won't be different. But for your own understanding, initially, break all the bonds and form all the bonds. So let's start breaking the bonds. So on the reactant side, this will be the energy that is taken in, right? The N
Yep.
energy. So the N energy, I have to break what? Which bonds do I have to break? I have to break 1 times this carbon-carbon double bond. So I'll write 1 times carbon-carbon double bond, the bond energy of carbon-carbon double bond plus. What else do I have to break? I have to break carbon-hydrogen bonds, 1, 2, 3, and 4. So 4 times I have to break the carbon-hydrogen bond, right? And 1 time I have to break the HBr single bond also. So plus 1 times the hydrogen bromine single bond. This is also the bond I have to break. So this is all the energy that is taken in. So all the reactants I have broke, all the bonds. Now I move on to the product. So you have only one product, and in that product, how many bonds do you see? Which type of bonds do you see? So minus energy given out. So you have to form how many carbon hydrogen bonds? 1, 2, 3, 4, 5. 5 carbon hydrogen bonds. 5 times carbon hydrogen bonds plus what else? Carbon carbon single bond 1 times. So 1 times the carbon carbon single bond plus how many times the carbon bromine bond? So you have a carbon bromine bond also. So 1 times the carbon bromine bond also. These are the bonds that are going to be formed. So now what do? I plug in the values. So delta H naught of reaction would be equal to 1 times, what is the bond energy for carbon-carbon double bond? That's 350, right?
For a single one, yes.
Yeah, no, for the, sorry, for the double bond. We're
It's
inserting double
610.
bond over here, right?
Yep.
So that's 610 plus, what's the bond energy for carbon-hydrogen single bond? That's 410, so you have to do 4 times 410 kilojoules plus what else? 1 times hydrogen bromine bond, that's 366. So 1 times 366. This is all the energy that will be taken in into breaking bonds. And what's the energy given out? So 5 times carbon hydrogen bond. So 5 times what's the bond energy for carbon hydrogen? That's 410. 5 times 410 plus 1 times carbon carbon single bond. Where's carbon carbon single bond? 350 plus 1 times carbon bromine. What's the bond energy for carbon bromine? It's 280. So 1 times 280. Now I solve the brackets first. So delta H naught of reaction would be equal to, again, Do not write the answer of 4 times 410 over here. Initially, you want to show the examiner that you use this value and you use the 4 multiplier with it. Otherwise, you lose 1 mark over here, okay?
Yep.
So what's the first bracket's answer? Just plug it in as it is in the calculator and then calculate what's the total.
For the whole first bracket?
Yeah, for the whole first bracket. So it's 610 plus 4 times 410 plus 366.
2,616.
20
2616.
2616 and positive, right?
Yep.
And then minus, what's the second bracket? It's 5 times 410 plus 350 plus 280.
2680.
So it's positive 2680, right?
Yep.
And since this is released energy, and I catered for that in this formula, remember that. The formula was plus minus released energy. I made it minus released energy. So when I open this bracket, it automatically becomes what? Negative energy, right? So
Yep.
that's why I will just plug in the values. I'll calculate the answers. And now when I open the bracket, its delta H naught of reaction is equal to 2616 minus 2680. So this is now the released energy. So what would be the answer of this?
Negative 64.
Negative 64, and the unit would be kilojoules per mole. Now, what have we calculated? We have calculated the enthalpy change for the reaction. So for this reaction, the enthalpy change or the overall energy change is negative 64. Clear?
Yep.
So this was what we had to do in bond energy questions. So I'll give you the example that we did yesterday. We did not put any values in it. So it's N2 plus 3H2 goes into 2NH3, right? So it says the data that you've been given is, or what is the data that you need? Let's take it out from the data booklet ourselves. I'm telling you that you have to use bond energies over here in order to calculate this delta H naught of reaction. All right, this is what I am going to tell you. So use bond energies to calculate delta H naught of reaction. Now you have to figure out the data yourself. What's the first step? You open up each molecule in your equation and you see what bonds are present over there. So nitrogen gas, it's nitrogen, nitrogen, triple bond. And since you have 1 mole over here, just make it 110. Plus hydrogen gas, it's hydrogen, hydrogen, single bond. How many times? You have 3 moles of hydrogen gas, so draw it like this. That goes into 2 moles of NH3. NH3 is nitrogen with 3 single bonds with hydrogen. You have 2 moles of this, so make it 2 times. So NH, H, and H. All right, this is our reaction. We have opened up each molecule and shown the Lewis structure or the bonds that are present over there, and we have to calculate the delta H naught of reaction. What are the bond energies that I'm going to need from the data booklet? Yep. So let's first
The
write the
hydrogen
equation and
bond?
then we'll know. Let's just write the equation first. We'll solve this. So we know we need to use bond energies. So let's write the equation for delta H. Delta H is equal to in energy minus out energy. Right? Break every single bond, form every single bond. So let's go on to which bonds that you have to break. You have to break what? 1 times you have to break what? Nitrogen, nitrogen, triple bond. Plus, how many times you have to break the hydrogen, hydrogen, single bond?
3 times.
3 times. So 3 times the hydrogen, hydrogen, single bond. Plus, do I have to break anything else?
Yep.
What else do I have to break?
The nitrogen hydrogen bonds?
That's on the product side. That's not the
Yep.
energy in, that's energy out.
Yep. But
Right?
in the
So
out,
the
right?
in
Yep.
portion is done. The reactants are done. Now on the product side, I have these bonds. So nitrogen, hydrogen, how many times?
6.
6 nitrogen, hydrogen bonds. So 6 times the nitrogen, hydrogen bond. So now I know which bond energies I'm going to take from the data booklet. Which bond energies do I need from the data booklet? I need nitrogen-hydrogen triple bond. I need hydrogen-hydrogen single bond, and I need nitrogen-hydrogen bond energy, right? So let's go and look for nitrogen-nitrogen triple bond. Where is nitrogen-hydrogen triple bond? It might be on the other page. Yep. So nitrogen-nitrogen triple bond is 944. Let's label that over there. Go back. And what else do we need? We need hydrogen-hydrogen single bond. That is 436. So 436, and we need nitrogen-hydrogen single bond that I saw in the next page. So nitrogen-hydrogen single bond, it's over here. That's 390. So this was the data that was supposed to be given in the question. But if it wasn't given in the question and we were asked to use bond energies in order to calculate the delta H naught of reaction, you could always go to the data booklet and pick out the relevant bond energies that you need after writing the equation and this form of the equation in which you mention each bond and how many times you have to break that bond. So now I can solve this. Delta H naught of reaction would be equal to 1 times the nitrogen-nitrogen triple bond, that's 944, plus 3 times the hydrogen-hydrogen single bond, that's 436. That's all minus, and then 6 times the nitrogen-hydrogen single bond, that's 390. So now what is the first bracket? That's 944 plus 3 times 436.
Two.
Minus 6 times 390.
2340.
So delta H naught of reaction would be equal to how much?
Negative 118.
180 kilojoules.
No, 118.
118.
Yeah, 118.
All right. So 118 kilojoules per mole. Are we clear? So bond
Yep.
energy questions are very easy. You just have to be able to pick out the correct bonds, and for it to be make it easier for you, just do what? Break all the bonds and form all the bonds. That will make it very easy for you in order to calculate bond energies. All right.
Yep.